Hello, everybody.
Hey everyone.
Hi everyone.
Good morning and good afternoon for everybody, and good night for, of course, our friends of India. I think this is the sixth webinar we have done in 2025, right, Emi?
Yes, you're right. The sixth week that we are providing this webinar, and it's a good way to learn.
Yeah, and this is the first with Jonas. We have today Jonas. Sorry, but I'm very bad pronouncing your last name. I know it's hard pronunciation.
It's Jonas Muehlethaler.
Jonas
Yeah,
Muehlethaler.
it's difficult outside Germans speaking parts of the world. It's difficult to pronounce it.
Right. So this is good because next week you are going to be at APEC in Atlanta. This famous event for electronic engineers about power electronics. And what do you can share with us about it? What are your plans there?
Yeah, I'm looking very much forward to the APEC. It's now the third time in a row that I'm attending with Frenetic. Before I was also attending at ETH Zurich and from other jobs I had. I'm looking forward to different things. For instance, the PSMA workshop, which I think is on the Saturday before the APEC, the actual APEC. I will be there. Of course, I will be very often at the booth. So whenever Frenetic has a booth, whenever you have something to discuss or you would like to meet, feel free to join us. I also have a little publication. I did some research in the field of core losses that I think I will present on Thursday at the last day of the APEC. So full packed, but looking forward to it.
Sounds great. Sounds great. Yes, we know that you have been preparing many things there to be there, Jonas. Well, it's just in a couple of weeks, so that's good.
Next week.
Yes. Well, today we have almost a week. Yeah. Well, today we have this as you have received by joining this event with your work email. We are providing access to our last product that is called Frenetic AI that also Jonas will be showing today. And also this, as you will see, our product is linked with our with other product that is Frenetic Simulator. And as you know, we are launching this, we are crafting this new tool. So you have already received in your email your credentials to access to this platform. And you will see now the demo. And together with the credentials, you have a link to a page where you can see the first use case that you can share. And now I would like to ask for some help that, as you know, we build products that really help power engineers. So we build together, we co-create this tool, and your feedback is really, really important for us. Now I'm seeing that many attendees have provided feedback to us, and we have already implemented some of their improvement and their suggestion. I would like to share, if you can, in the chat, just write yes if you would like to jump in a quick session of 15 minutes to provide some feedback after you try our tool, because we will show you in advance some premium features that we are preparing, and your feedback is really, really helpful for us. We will contact you, and we are promoting this, and also we are giving you some access to our simulator in order to thank you your effort to be here. And we would like to build something beautiful. We would like to build something powerful. So the best way is to build in community. So thank you a lot for joining.
Okay, Jonas. So the stage is yours. So if you want to start now, or you want to share anything else before started, up to you.
Well, I think I can start with the presentation. Let me share the screen. A very, very short presentation, but then we will go into a demo. The objective today is to show you how to design a boost inductor with Frenetic AI and Frenetic Simulator. Exactly. So before doing this, I would like to very briefly show you what is actually Frenetic AI. So what is our objective? So Frenetic AI is kind of an AI-powered assistant for power converter design. So those who know Frenetic from several years already, we are very strong in magnetic design, so transformers, inductors, and so forth. But we also added a layer on top of that, or we are currently adding a layer on top of that that helps the user to first design the converter itself, and from there dig deeper, either going to simulations with circuit simulators like LT-Spice, or going to Frenetic Simulator to build a magnetic component or design a magnetic component. So the backbone, or this was Frenetic AI. This is kind of the power electronics layer. If you go dig a bit deeper, then we see here Frenetic Magnetic Simulator. So this is our tool that allows to design and optimize magnetic components. It's an online software for simulation and design. As I said, supports common topologies for power electronics. Most topologies are in there, a lot. And we have also a laboratory in Madrid and a little laboratory also in Zurich. So we validate all our models that we integrate here. I gave some seminars before about the models itself, but today we focus not so much on the models, but more on the application here. There are many use cases. You can read here yourself. Basically, if you design a power converter, and most likely you also need a magnetic component, then Frenetic is the place to go. I wait a little bit, maybe if you want to have a demo for Frenetic Simulator, but also from Frenetic AI, request a personal demo, not just a demo like I do now. Maybe you can quickly take a photo of this QR code. Exactly. So what we were thinking is, well, how is the process of designing a power supply, a switch mode power supply? And usually, let me take the pointer here. You start with specs, then you have to select your topology. You go into circuit design and simulation. You select the components, you do your magnetics, you measure samples, and then you go to do actual hardware tests. And so far, we focused mainly here on the custom magnetic design, but with Frenetic AI here, we try to cover end-to-end kind of the design process of a magnetic component. Another picture that shows this is our Frenetic AI that is then connecting other tools, which at the moment is the Frenetic Magnetic Simulator. LT-Spice can be connected. There was a webinar about this tool. And these are in brackets because they are not yet implemented, but these are things we have in mind, and there are many more ideas that we have in mind that we could cover in the future by building such a platform. Now today, I would like to show you how to design a boost inductor, PFC, a boost inductor of a PFC rectifier. What is a PFC rectifier? Basically, it's an AC-DC converter. You have a AC mains here. You rectify this, and then you have a subsequent boost converter that is controlled in a way that the output voltage here is as stable as possible, but it has to be higher than here. I will show this now in how we're doing this. Let me change to the demo. So I will now quickly go out of this presentation. We are not yet at the Q&A session. Sorry for that.
Yeah, the Q&A part is at the end.
It's at the end. So we're at the demo part here. So let me, you still see my screen, right? So let me go. So I started Frenetic AI. Basically, you have, all of you, as I understand, have now access to it, at least the one with a company email address, got an email from us. So you can play and try what we show here on your own. Basically, it's pretty straightforward. You put your requirements in, you choose your topology. If you don't know your topology, you can also have the tool suggest the topology for you. Then you confirm the data, and it calculates a design or a converter for you. Let me show this, how it's done. What I would like to show today, which may be something which is also possible, you can also put ranges in there. So often you design a converter for one operating point, but then it's also, you would like to have that is operational on another operating point. So what you can do here, put ranges in there. You can also, let's put here an output voltage, 400 volt, 500 watt. This is just an example of a, let's say maybe more for industrial purposes, a PFC converter. Now, if you think 110, I didn't choose these values by coincidence. 110 volt is the grid in the US domain, but there you have 60 hertz. So you can also add additional comments here. For instance, the grid or F grid for 110 volt AC operating point is 60 hertz, and grid frequency, sorry, I have to make it correctly. Grid frequency for 110 volt operating point is 60 hertz, and grid frequency for 220 or 230 volt operating point is 50 hertz. So that this is more the European or system. So I choose now PFC because I know PFC is the topology I want to go with, and I confirm. Now we have to be a bit patient, but it's calculating now, or it's doing a circuit design for us. You can also, if you don't know the voltage, let's say you do you want to have another application, let's say 230 volts to USB-C. You want to build a USB-C outlet. You can also just put output voltage USB-C or any standard, and it will then consider this. So we have already our design. So this is our design that came out. So you see here, switching frequency, it shows 100 kilohertz for us. If you don't like 100 kilohertz, you can also change this by just adding a comment to the chatbot or to the field up there. You see here current, the inductance is of course the same because we want to build only one converter. So we have one converter that suits both operating points. The input current is lower when you have higher voltages, and the grid frequency was adjusted 60 and 50 hertz. Now you can do different things. You can, for instance, generate an LT-SPICE model. I can quickly show this. When you generate a LT-SPICE model, it now builds an LT-SPICE model of this converter with this inductor in here. I think we already had a webinar showing this, so I will very quickly just show how it is, how it looks like. From there, you can maybe start your control design. So if you want to do, at the moment, our LT-SPICE files are open loop. You can now build your closed loop control to the design if you want. You have to be a bit patient here. So we have now a design. I load it. This is the one. And I can show that it's working nicely. All right, but okay, that's not the objective of today. Today we would like to make a magnetic design. So I press a button such as magnetic design. Now this time it's not AI based. We took all this information and call a Frenetic simulator. So the magnetic simulator I showed at the beginning, and the magnetic simulator will now provide us with a suitable magnetic design. Again, it's not infinite fast, but it will lead to a very good design. Exactly, so now it's loading the design, and you see here, it took me a ferrite core with the material 3C95, PQ35. Maybe some of you might think powder would be a good option, but I think the switching frequency is quite high. So because of the high switching frequency, ferrite is a good material. You see already some preliminary results like the losses and the maximum temperature. It's typical that in case of PFC that the losses are not balanced. I can explain a little bit why this is the case later. Anyhow, so now this is kind of, so far it was Frenetic AI, but I would like to now work on this design. Maybe I'm not 100% happy. So let me try to, or let me load this in Frenetic Simulator. At the moment, we do this through putting our email address here, but this is an email that is registered. You have to have access to Frenetic Simulator in order to do the next step. I can now save this design, and the design has been created successfully. So I change now the design. I'm here in Frenetic Simulator. I have to reload this page. This is the inductor that we just designed, and I load this inductor, and it works nicely. So what you see here now, this is jumping from Frenetic AI to Frenetic Simulator. So this is the other tool we have. Frenetic Simulator is a tool specifically tailored for magnetic components. So it allows you to put in like all your converter requirements, but you have to know your inductance value, for instance, in this case. So you have to know this in order to build the magnetics. You can also have an automatic suggestion feature. So you can also generate your design, but I will not do this because we did this already through Frenetic AI. You have some other tools that help you to design a converter. You have the core tab here. You see everything about the core, what you have chosen. If I click run, I can also see here, I have to quickly simulate it. You see here where it saturates. So it's not a problem for our case. You see here the winding page, what in this case Litz wire was selected. The reason for Litz wire here is you have a fringing field, leads to high proximity losses, or a lot of layers also lead to high proximity losses. So we need a good material here. Not material, a good copper wire, like a Litz wire here. And in this particular case, I will not talk about the models we are using here, but we have quite accurate models in the backbone of this converter, such as things like fringing field for air gap is considered, or also the inductance calculation has an air gap model behind. So this is our circuit simulator. Let's say I would like to change a little bit. I'm not happy with this design. I would like to, let's say, try to go for a smaller design. I tried this before this call. It was not possible for me to get a feasible design that is smaller. That means we are here almost at the boundary, like it's the most compact design that is possible, or one of the relatively compact design. You see this also at the temperature. If you go smaller, then the temperature would reach too high levels. So, but what you could do, for instance, just as an example, I would like to try a bigger core. Why would I try a bigger core? Often bigger cores have higher efficiencies. Higher efficiencies are something that I want, because I trade space with give a bit more space, but then have a higher efficiency of my converter. So I just choose a number bigger. Now, if I do this at the same time, my wire might change because I have now a bit more space for the wires. So I click here, suggest wires. It suggests me a new wire combination. So similar, but not exactly the same as before. Now, the only thing which is not correct, because I just changed the core, but I kept the turns ratio. You see here I have a too high inductance. So we have here a little toolbox, which is called the inductor calculator. Let's say I would like to know my air gap that I need to have, again, my 311 microhenry. 311 microhenry was the objective I have. So I calculate this. I see my gap that I need is 2.08, and I change this. Now I have a new design, a little bit bigger, and I will do a run it. And you see the results now, the losses are lower. Before the losses were around 3.7 watts, but here the losses are only around 2 watts. So that was our objective, right? I went to a bigger size, so it's not just it's not that this design is better than the other one, but it's another design that has a higher efficiency, and also the temperature is a bit different. Maybe just one comment: why are the core losses so low? This is a bit typical for PFCs. The reason is we have here 50 hertz, or in this case 60 hertz ripple. That almost leads to no losses, and then a relatively small flux swing on top of that, and that leads to very low core losses. This would be a bit different for powder cores, but for this ferrite core, it seems to be the case. Now, this design is finished, but not completely tested. Another feature we have is that we can test this at different operating points. So let's say I have this operating point from before, but you remember at the initial stage, I would also have, this should also work with 230 volt and 50 hertz. So I have now 2 operating points, and I would like to see whether it's a suitable design for both cases. I could also add a third point. Let's do this, maybe a 200 watts, so a low load and a low load condition, so not at maximum load. So I have now 3 operating points. I can add many more. And let's run this again. So it's finished, and I go to my design summary, and you see here a lot of information. Let's go through them very quickly. We have the 3 operating points, then the inductance, switching frequency, all the waveform characteristics. There, well, the inductance is the same, but the rest changes, of course. Then we see here the losses. You see how the losses changed from one operating point to the other. That I think there, I have to say, there is a little. Let me check this. Let's run this again. I want to try something. I'm a bit confused that the winding losses are the same in 2 operating points. Something, maybe there is a small bug here. Yeah, it was different. Probably I didn't loaded the waveforms. I forgot to load the waveforms after defining the operating point. Okay, so now it's clear. The winding losses go down when I increase the output voltage. I have lower current, which you can see here, and by these lower winding losses. Yeah, so like this, you have an overview on your operating points, and you go through this. You have also at the end small data sheet where everything is summarized. For instance, a bill of material, how you connect the windings, and so forth. Okay, so I'm aware I went very, very quickly through all these tabs, and maybe it was difficult sometimes to follow everything. So we were very happy to have a personal presentation about this tool. So, but I think you get the point. You start on a more high level, the whole power electronics part, you get very quickly to a very good design, but then you can fine tune it to your needs through the other tool we are having. Okay, that was the demo. I will now, I don't know if I find the last slide, but basically that was the slide. But I think I would hand over to Q&A.
Yes, thank you, Jonas. Many questions. We'll start with some of the questions here. That yes, we can we use the Frenetic simulator for a topology that is not included in the preset ones? Yes, because we have some in our simulator. We have let's say a generic topology or a generic case that you can customize as desired for inductors and also for transformer. That's answer. And
There
now
is
we have
just,
another
can I
question.
make a
Yeah.
comment? One person said
Yeah.
there is 120 volt, not 110 volt anymore in the USA. Sorry for that. I'm located here in Switzerland, Europe. So I hope, yeah, sorry for that.
Yes, it can be highly customized. And one question, Jonas, here is, what is the location of the expected temperature that we show in simulator? Is inner surface?
Can you repeat the question?
Yes. Could you highlight the location of the expected temperature shown in the simulator? Is it inner or
Of the
surface?
magnetic component? It's
Yeah.
the inner winding. Okay. Let me share again the screen.
Yes. So you said, can be clarified.
Well, we calculate, yeah, that's a very good question. This is the maximum temperature that we calculated, this one here. We have the core temperature, but the maximum temperature is usually at the inner side of the winding. So yeah, we calculate winding temperatures and core temperatures. Sometimes you have multiple windings and multiple core temperatures, but depending on the core shape, but then we take the maximum, which can be core or winding. But in this case, it's definitely winding, and it's for sure here inside at this point here, close to the gap where you have high fringing field effects. And like this, you have here a lot heat generated, which has a bit problems leaving the core.
Okay, great. And let's see about one more question. There was related, what are the main difference between using Frenetic simulator versus something more in deep like ANSYS Maxwell?
Okay. I will share. So what is ANSYS Maxwell? ANSYS Maxwell is actually a finite element tool. So you would build a 3D model of the whole core, which is then consisting of the core plus winding. And it takes a lot of time to simulate, but you reach, at least in the winding domain, a higher accuracy with ANSYS. But ANSYS is not really a design tool. It doesn't help you to start from here and get quickly to the optimal core and to the optimal winding. But if you want to now know exactly the temperature at each of these points here, then it makes sense to switch to a finite element approach, which can be provided by ANSYS or COMSOL or other tools. We have also a button here, ANSYS model, so we can also export our devices into ANSYS, because some of our clients, they need to go this additional step in some cases. But in very many cases, it's sufficient to have more analytical equations to get high-level results, let's say like this. I hope I was clear with my answer.
Yes, thank you, Jonas. I think that we are on time. We are 2 minutes late. We have some other questions that we will contact you to answer the set of question, and also we will contact the people that has offered to share feedback. This is the way that we will keep creating many things that will help you in your journey. Keep updated about our new webinars that we'll be bringing in upcoming weeks. So thank you a lot for being there and your collaboration. I know if you have any other words, Jonas and Eddie.
I wanted to say something after before finishing this webinar. There are several people with the same question about how we can get a free trial about the Frenetic simulator. Okay, what we are giving access is for the Frenetic AI. This is completely free for you at this moment. So I have shared the link to the waitlist, and there is a good way to get one free week access to the Frenetic simulator. Is once you have used the Frenetic AI as user, accept a call for feedback about Frenetic AI with our product team. and you will gain 1 week of free access to the simulator. So that is correct, right, Emmy?
Yes, this is correct. The idea is that if you can join a 15-minute quick call in order to get feedback about the usage of Frenetic AI, and also we are presenting some premium features that we are going to release soon. We gather that feedback and we join in that meeting. You will get access to our simulator too. That, as Jonas has already shown, this is our platform, so all our products are joined, so you will get the access to.
Okay,
I
great.
think that we are ready.
Yeah, okay. To finish, thank you to everybody to connect today. Thank you, Jonas. Thank you, Emmy. And for all attendees, you will receive the recording between today and tomorrow. So don't worry. And if you have any question, don't hesitate to respond directly to that email.
Great. Thank you a lot for being there.
Thank you very much.
Thank you.
See you soon.
Bye bye.